Yes, hi everyone. Welcome to VSA Online, and I hope this time shift to winter time, at least in Europe, wasn't too confusing. At least in Europe, we start 1 hour earlier than during summer. Anyway, so I'm very happy to host Anthony Thomas from UC Berkeley. So I need to correct the previous announcement. So without any further delay, so Anthony, the floor is yours, please.
Okay, great. Yeah, thank you. So let me just share screen here. Great. Okay, yeah, so thanks for the introduction. I'm Anthony. I'm a postdoc at the Redwood Center at UC Berkeley. And I just recently completed my PhD at UC San Diego. And so most of the stuff I'm going to be talking about today is based on the work that I did during my PhD. So the basic premise of the talk is my sort of original background is from machine learning. And as I was sort of going through VSAs and learning about hyperdifferential computing and VSAs, I sort of noticed that there are a lot of similarities between concepts that appear in VSAs and concepts that appear in the sort of broader machine learning canon. And so the motivation of the talk today is to just kind of try and take a first pass at fleshing out some of these areas of connection with the hope of sort of better understanding like what is out there in the broader literature and what tools it can provide that helps us to understand VSAs. So I think we're all familiar with VSAs and hyperdimensional computing, and I'm going to use those two terms interchangeably in the talk today. But the basic idea, of course, is that in HDC, we perform computation on these distributed representations of data. And the idea is that we have some sort of input that could be, say, like text, feature vectors, or structured data like graphs or time series or something. And then we embed this data into these high-dimensional distributed representations using this encoding function. And so sometimes the encoding function may consist of several different steps. Like we could have embeddings of individual atoms, like characters or nodes in a graph that we then compose to form an embedding of the complete structure in some way. But the basic idea is that at the end of the day, what we end up with is this high-dimensional vector that represents whatever our piece of input data is. And so there are a number of things that are very appealing about this paradigm. So these representations typically require low precision. And in fact, it's easy to show that you can always find a representation that is low precision, that is sort of like good enough in a certain sense. The representations are fault tolerant in the sense that if we like flip some of the bits in the representation, it doesn't destroy the meaning of the vector. And the operations that we use to manipulate these vector representations of data are very easy to parallelize. And so what this means is that the technique is very well suited to implementation in low power hardware. In a kind of more abstract sense, one of the things that I find really appealing about this paradigm is that we use these sort of algebraic operators like bundling and binding that to build representations of more complex concepts from simpler atoms. So for example, if we want to represent something like the idea of a purple flower, we can associate the idea of color with the particular value of purple via this binding operator. And so what this is nice is that this sort of algebraic structure makes it very concrete what these vectors are representing. And so this is in contrast to other sorts of things like a deep neural network, say, which can also be interpreted as constructing a vector representation of your data. But there, the representation is sort of, it's much more difficult to understand like what the representation is telling us. And this sort of algebraic structure of this model is very, sort of makes it very easy to understand like what these vectors mean. So in addition, I think like, for this broader goal of transparency, beyond having this sort of intuitive property of algebraic structure in the representations, we also want formal guarantees of correctness. So what I mean by that is what we say oftentimes is we construct these embeddings of data and then we run some algorithm on them. Like we fit a linear separator, we use them to do classification, we use them to sort of perform various tasks. And what we want to know is when is the output of that algorithm correct? And so we have these kind of guarantees for traditional CS algorithms. Like, if I run Dijkstra's algorithm, there's a proof that I can encapsulate the algorithm's desired behavior in a theorem statement, and then I can prove that that theorem is correct. And so we would like to have similar sorts of results for hyperdimensional computing and VSAs. And that's sort of generally the interest of my work. Now, in fact, we do have very good theory for this kind of a question in a specific case, and that's for the case of answering membership queries. So the idea of a membership query is to say, given a superposition of objects, we want to detect if a particular query example is present in the superposition. So for example, like let's say that we just observe a collection of discrete objects. So here, the universe of objects that we try to represent are native animals of California. And so of course, we're all familiar with the scheme in which we assign each object some code word, say by sampling the code words uniformly from the d-dimensional cube. And then to represent a set or a collection of objects drawn from this universe, we just bundle or sum together their code words. So to represent the set of birds, we bundle together the code word for sage grouse and the code word for bald eagle, and that gives us a representer of the set. And then we can ask membership queries by looking at the value of a dot product between the embedding of a query and the embedding of the superposition, or sorry, the superposition of the embeddings. So for example, if we want to ask the question, is a bald eagle a bird? We just look at the value of the dot product between the embedding of the bald eagle and the embedding of the set of birds. And the hope is that that value is big if and only if a bald eagle is in fact a bird, which of course it is. So there's a long line of literature on developing a theoretical understanding of when these kinds of queries will be correct. So when these sorts of membership queries will be answered correctly. And this allows us to relate things like the size of the universe from which sets are drawn and the size of the sets themselves to the probability of answering membership queries correctly. And I'm sorry if I missed anybody's work in here. These are just the sort of these are just the four that immediately sprang to mind. But of course, there's a wide variety of other problems we might be interested in solving with VSAs or HD computing. So say something like regression, where given the embedding of a symbol, we want to predict some sort of continuous output associated with it. Similarly, classification, which could maybe be interpreted as a special case of regression, or clustering, where you want to do something unsupervised. And so the idea here is like what we want to know is how do architectural decisions about the VSA, like the choice of encoding dimension, how precisely we construct this encoding function, how do these kinds of decisions affect our ability to perform these tasks? So the basic claim of the talk today is that, in fact, the sort of basic paradigm that is espoused in VSAs, in which we take data, embed it as high-dimensional vectors, and then use some sort of like algebraic operations to manipulate and combine these embeddings, I think is actually a sort of ubiquitous paradigm in machine learning. And I would go so far as to say it is one of the dominant paradigms of machine learning. And so we can sort of broadly think of this as falling under this idea of a sort of blessing of dimensionality, where on the sort of original version of the data, a task is difficult to perform for some reason. And this high dimensional embedding exposes some sort of notion of latent structure in the data in such a way that these tasks become easier to solve. And so this idea appears all over the place in the machine learning canon. So in particular, today I'm going to be talking about kernel methods, which are primarily from the literature on statistics and machine learning, randomized embeddings and locality-sensitive hashing, which come from computer science, and of course, the thing we all know and love, hyperdimensional computing, which originated in the cognitive neuroscience literature. And so my basic claim is that these things are all sort of getting at a kind of similar underlying idea in sort of different ways. And the idea is to understand like, well, what is similar about these and what is different? And so one thing that I really want to emphasize here is that the literature on these topics is really, really large. So I was just sort of curious, and I typed each of these keywords into Google Scholar. And of course, this isn't a very super scientific way to understand like the exact counts of papers or anything, but just to kind of give you like a rough sense of what is out there. So there's about 4.6 million results on these three different areas. And for context, that's about twice as many as there are for hits on deep neural networks. And of this, the overwhelming majority is devoted to kernel methods, and I'll talk a lot more about those later. But I think the basic point is just that there's a lot of stuff out there. And so it's worth it for us to take some time to understand what it contains. So sort of more specifically, I think like, we in the VSA community should really be interested in this literature for a few reasons. So for one thing, these kinds of techniques like kernel methods and randomized embeddings are really sort of like foundational and bread and butter techniques for theoreticians in communities like machine learning, statistics, and applied math. And so, being conversant in these kinds of tools will help us to engage and being able to explain our own ideas, and provide a sort of anchor point in these kinds of techniques will help us engage with these kinds of theory communities. There's also a very large theoretical literature that provides exactly these kinds of rigorous bounds and guarantees that I was talking about earlier. And we can import a lot of this literature almost directly into the VSA setting. And then finally, this sort of will help us understand like what is it that VSAs really stand to contribute to this broader paradigm. So the goal of my talk today is to just give you a sort of like survey style overview of a very, very small subset of this literature. Like, there's literally millions of papers written about this, and I will only be able to cover a tiny, tiny slice of everything that is out there. But hopefully it'll give you a sort of sense of like what these different paradigms are and how they're similar to VSAs. And of course, I don't claim to have been the first person to notice this. There have been many people who have observed that VSAs are related to these other areas, in particular kernel methods and random projection. So my goal is really to just kind of like tie together a lot of the observations that have already appeared in the literature into a sort of like unified talk. So in general, we typically motivate encoding by saying that what we want encoding to do is preserve similarities in some way. So what we want is that data that is similar in its original representation should be similar in its embedded or HD representation. And in practice, what this usually means is that we want inner products in HD space to be big for inputs that are similar in the ambient representation and small for dissimilar inputs. So for example, if we have pictures of dogs and cats, we would typically want the embeddings of the dogs to have a higher dot product, than the embeddings of the dog and the cat. So let's see a couple examples, how this arises naturally through some of the encoding methods that we're probably already familiar with. So like we said before, the sort of most, the sort of prototypical example of VSA is when we just have a collection of discrete symbols. So the thing that we all know to do is that we associate each symbol with this d-dimensional code word. So for example, by sampling the code word from the d-dimensional unit Q. And of course, just as a sort of consequence of this pseudo-orthogonal property that we're all familiar with, the idea is that these code words have the property that if you look at a dot product between the embeddings of two different symbols, then they are non-zero or significantly non-zero if and only if the symbols are distinct, or sorry, the same, the opposite of what I said. So what we're saying is that we have this underlying notion of similarity, which is just the identity function that tells us are its operands the same or are they different, and an expectation over randomness in this in the generation of these embeddings. We're saying that dot products in HD space recover this underlying notion of similarity. And of course, we can extend this from sets consisting of one element to sets consisting of more than one element. So if we have a set that's drawn from an alphabet, say of size m, then we would represent the set by summing or bundling together its code words. And if you just do a little bit of simple algebra, you can show that what this is doing, if you look at dot product between the embeddings of two different sets, what it's really telling us is the size of their intersection. So the implied measure of similarity when we look at dot products in HD space is the size of the set intersection. And that's a reasonable thing to do given two encodings of sets. So oftentimes we can describe our data by collections of features that can take on different values. So for example, instead of thinking about our native California animals as just atomic objects, we could think of them as being described by sets of different feature value pairs. So for example, like what type of animal is it? Is it a bird or is it a fish? What does its plumage or scales look like? Where does it live? And so more generally, we can think about this as a situation in which we observe a collection of features that are associated with a different collection of values. And what we want to do is represent objects as sets drawn from this product alphabet of features and values. And so the way we do that is by binding. So we associate a particular feature with its value by binding the embedding of the feature with the embedding of the value. And then to represent a set, we just bundle together these bound pairs. And so implicitly what we're doing is constructing representers for symbols in this product alphabet. And the thing that's nice is that we're able to do that efficiently on the fly by binding instead of needing to explicitly materialize embeddings for every different symbol in this alphabet. But the underlying intuition is that in the same interpretation that if we look at dot products between embeddings of these sets, it gives us a notion of set intersection still applies. So we can also play this kind of trick for data that has some sort of like more complicated kinds of similarity structure. So for example, let's say that we observe a collection of points that are real numbers that are bounded between 0 and 1. A common way to encode this kind of data is using this thing that's variably called thermometer codes, scatter codes, or ID level encoding. And the idea here is that we just discretize support of each feature into a set of bins, and then we assign the bins code words such that the dot product between the code words is reflective of the distance between the bin centroids, or like the obvious notion of distance between the bin centroids. And so we can again just treat this as encoding a set of feature value pairs. And if we use the same encoding method I described previously using bundles of bindings, we can again show that the implied notion of similarity in the underlying data is based on L1 distances. So basically what we're saying is that in all these methods is that the encoding operation is a way to express some underlying similarity function of interest via dot products between these embeddings. And so I think the kind of crucial bit of intuition is that the encoding function is typically random in the sense that some aspect of the encoding is instantiated randomly. So for example, we draw these code words representing symbols from like the uniform distribution over the cube, or we generate the representers of these these like correlated representers for different bin centroids by like randomly flipping some number of bits. And so there's some notion of randomness involved in the encoding. And typically what we want is that in expectation over that randomness, we recover some sort of underlying similarity function that we think is appropriate for our task at hand. So in fact, there's a very large literature in machine learning on designing representations of data that have this property, where if we look at where we have some sort of random map to a higher dimensional space, and if we look at dot product between embeddings in that space, they recover some underlying notion of similarity on the data. And the techniques for doing this look in many cases quite a bit like the techniques that we use in hyperdimensional computing. So this literature arises under a variety of different names. Sometimes one sort of example is this area called locality sensitive hashing. There's also random projection and random Fourier features. And so these techniques are all sort of approaching this problem in slightly different ways, but the basic intuition is very similar to what I described earlier with VSAs. So let's look at a couple examples of techniques from this literature. So another way that we could go about representing data that lives in Euclidean space is by this technique of random signs. So the idea here is that the input data are unit vectors. So they're vectors that lie on the unit sphere. And the way that we embed this is by drawing a bunch of random hyperplanes. So these W's, the W1 through WD, that are sampled from the uniform distribution of the sphere, these define the normal vector of a random hyperplane. And then we just look at what side of the hyperplane a particular point falls on. So we can think of this as sort of like, so this embedding gives us a map from our data space to the d-dimensional cube. And it's just telling us, we can sort of think of it as like a hash of the data onto this high dimensional binary vector. And the idea is that if we look at dot products between these codes, they tell us the angular similarity. And the reason for that is very simple. What we're saying here is that like we're just asking how many of these random hyperplanes separate a pair of points. So when we do this dot product, really the question we're asking is like, out of these hyperplanes that we drew, how many of them are separating the two points that we're interested in computing the similarity for? And the probability that happens is directly proportional to the angle between them. So that method of similarity preserves angular distances, and we can extend it to preserve a more diverse type of distances between data using this technique called random Fourier features. So the basic idea here is that now we have points that are just arbitrary m-dimensional vectors, and we sample these weight vectors. Instead of sampling them from the uniform distribution over the sphere, we sample them from the m-dimensional isotropic Gaussian distribution. And then we define an embedding in a very similar way to what we did before, where except instead of taking the sign of the dot product along these different weights, we just do e to the I times that value. So it's this sort of like complex valued embedding. And via a kind of technical argument using a theorem from functional analysis, we can show that this encoding method approximates the Gaussian kernel. And so the key difference here is that by sort of messing around a little bit with how we define this embedding, we were able to get a different notion of similarity out of the data. And here where the underlying notion of similarity is based on the Euclidean distance between these 2 points. And so the kind of appealing thing about this particular notion of similarity is that it has this like rapidly decaying property where if 2 points are very, very far away, then their similarity as measured by dot products in this embedding space is essentially 0. And if they're very close, like if they coincide, then it's big. And in fact, we can extend this approach to work for any similarity function that just depends on the difference between its operands. And it turns out that this also has an interesting connection to Tony Plate's fractional power encoding. And there's a very nice paper by Pax and Frady that walks through this. So this particular embedding scheme is really widely used in machine learning, and there are many different variations on this theme. So one that some of you might have seen before is this alternative scheme in which we convert the previous embedding to a real valued representation by adding this random offset. And so this allows us to give an equivalent real valued embedding for the previous one. And then there's a third variant that doesn't appear as often, where you concatenate the sine and cosine of this thing. And so these are all just sort of different ways of realizing the same underlying similarity function. And that's sort of the kind of crucial piece of intuition, is that even though these embeddings sort of putatively look different, they're actually all doing the same thing, which is approximating the Gaussian kernel or some other shift invariant kernel by a dot product in HD space. So one question that that we're probably interested in is like, so what we've said is that we do this random mapping, and then in expectation over randomness, we recover this particular similarity function. But of course, that just is what happens in expectation. What we'd like to know is, like, what is the distribution over possible outcomes? So to look at that, we can sort of observe that many of these techniques conform to a broadly similar template. And the idea is that we design some sort of random function. And this is with just a scalar output. And the random function has the property that if we look at the expected value of the product between applying that random function to two inputs, it recovers the kernel. And so, if you want, you can just think of this as looking at like, v of x subscript I. And then the way we build the encoding is just by generating d independent copies of these functions. And then we estimate the underlying similarity function by an empirical average. So when we compute a dot product in HD space, we can interpret this as computing an empirical mean, and then just by the law of large numbers, that mean, as we take the encoding dimension to be sufficiently large, converges to the expectation, which is the true similarity function. And so the question then is, how should we choose the embedding dimension to guarantee that this approximation is good enough? And the literature on randomized embeddings supplies us with a lot of techniques that let us do that. And the way these arguments typically work is by using concentration inequalities. So I'll just walk through a sort of short example of one here. So let's say that we have a set of n points. And if we like, we can assume that they're points in Euclidean space. And what we want to guarantee is that the dot products between embeddings of these points approximate the kernel to within an additive error of epsilon. So it's saying like this xx prime should be xi xj. What we're saying is that over all possible pairs of points from our set of inputs, we'd like the maximum possible error and approximation of the underlying similarity function to be at most epsilon. So let's suppose that this underlying random function that we're using to generate the encoding is bounded, in the sense that there's some constant that for every x it's at most that value. And so what we can do is just apply this sort of standard concentration inequality called Hufting's inequality, which bounds the deviation of a sum of bounded random variables from its mean. What that tells us is that to guarantee that this condition holds, to guarantee that we achieve an epsilon additive error approximation, it's sufficient to take the number of random features, or the embedding dimension, to be on the order of b squared, where b is the bound on the component-wise bound on our embedding, over epsilon squared times log the number of data points. So the things to emphasize here is that really what this is telling us is that we can embed a set of endpoints into a space of just log n dimensions, 1 over epsilon squared log n dimensions, and preserve all pairwise similarity. So we're preserving the geometry of the set in a certain way up to additive error epsilon. And so in general, there's a very large family of techniques that can be used to obtain bounds that look like this. And the bound I showed here is just a sort of very, very simple example of how we can do this. And it's often possible to improve substantially on the rate that I've given here. And so I've suggested some good resources here that if people are interested in how to derive these kinds of high probability bounds, I've suggested some resources here that I think would be helpful. All right, so let's recap where we are. What we've said is that we've constructed this encoding, we've constructed this embedding so that dot products in the embedding space function as a noisy approximation to some underlying similarity function of interest. And in particular, what we said is that for most of these encoding operations, what we can say is that in expectation over randomness in the encoding, we recover some underlying similarity function. So this approximation becomes exact in this sort of like regime of expectations. And what we said is that different encoding architectures approximate different underlying notions of similarity. So why does this matter? Well, different underlying notions of similarity are appropriate for different kinds of tasks. So just to provide a sort of motivating example for this, one of the kinds of typical practical uses of HD computing is to fit classifiers. And so the way that we often do this is we say we have a collection of data that belongs to two classes. So let's say the data belongs to, the data consists of pictures of cats and pictures of dogs. And the way that we typically construct classifiers is by forming these prototypical examples that represent the class of cat and class of dog in some way. And so the most rudimentary way to do this would be to literally just encode all of our data and then sort of superimpose it together into a prototype for that, representing that particular class. But there are sort of other more sophisticated procedures we could use as well. And then to make a prediction, we just encode our query, and then we look at the value of a dot product between the embedding of the query and these two class prototypes. And then we just pick whichever one makes a larger dot product. And so the thing that we can observe is that this is equivalent to learning a linear separator in HD space. So no matter how we go about learning these particular prototypes, this decision rule amounts to a decision rule based on a linear separator. So what we said here is that for this procedure to possibly have any hope of succeeding, there needs to at least exist. I mean, succeeding in the sense that we correctly label our data, there needs to at least exist a linear separator in HD space. And that's a sort of absolute minimum thing that we should hope for. And so like, what do we need of our encoding function? Well, the sort of like absolute minimum that we should ask of it is that it at least not destroy linear separability to the extent that it existed in the first place. So what we're saying is that, like, if the data already is separable, at least that separability should be preserved in under the encoding operation so that this procedure, which is based on finding a separating hyperplane, will succeed. And so it turns out that that for this to be true, so for separability to be preserved under encoding, it's sufficient for the encoding to preserve dot products between input points. So what I mean by this more specifically is that if we have two sets of points that are separable with some positive margins, that means that their convex hulls are separated by a positive distance, then provided dot products in HD space approximate dot products on the original version of the data up to some error that depends on the margin, then there will exist a valid separating hyperplane in HD space. So why is this? Basically, the reason that this works is that an equivalent definition of saying that two things are separable is to say that their convex hulls are separated by some positive distance, and we call that the margin. And so there's this basic result from linear algebra which says that we can write any points on the convex hulls of two sets of any point on the convex hulls of two sets as a linear combination of at most m plus 1 points, where m is the dimension of the underlying data. And so what this means is that we can define a separating hyperplane on the ambient version of the data, the original version, in terms of these points P and Q, which we can represent as linear combinations of data. And then if we just embed these points P and Q, or we embed the points that are used to construct them by a linear combination, then that separating hyperplane will still work in HD space. But the idea here is that the encoding is a sort of noisy approximation to dot products. And so we have to ensure that the amount of noise is small enough that the separating hyperplane still works. And that's where this gamma over 6 condition comes from. So the kind of essential piece of intuition is that what we're saying is that the appropriate notion of similarity for our task, which is preserving separability, is a dot product. And so what we want is encodings to preserve that notion of similarity. We want dot products in HD space to preserve dot products in the original version of the data. But these are a noisy approximation, and so the amount of noise that we can tolerate is dictated by the margin, which is an intrinsic property of the data that we don't have control over. And intuitively, what this means is that if our data points are separated by a bigger margin, we can use a smaller encoding dimension and tolerate more noise. So that proof just guarantees the existence of a linear separator. We still have to actually obtain one from data. And in general, there's a very simple algorithm that will allow us to obtain a linear separator. And that's this algorithm, Rosenblatt's perceptron, that was first developed way back in the 50s. And the perceptron has the property that if a linear separator exists, the algorithm will return one after making at most a number of mistakes that depends on the margin and the length of the input data points. So we can bound the number of mistakes this procedure will make before it returns a valid separator for our data. So one thing that turns out to be really important about the perceptron is that we can represent the vector of weights that it returns in two ways. We can think of it either just as a vector. So this is just some vector in HD space, and it's just a vector. Or we can think of it in this dual representation in which we view it as a superposition of encodings. So if we look at the update rule, whenever the algorithm makes a mistake, it just adds in the embedding of the point in question times the label. And so that's just either adding or subtracting that point from the separator. And so we can view the weight vector as this linear combination of encoding of data, where this coefficient alpha is non-zero if and only if the algorithm made a mistake on xi. And so we can think of this kind of intuitively as like a filtering algorithm on a stream. So let's say that we have a big collection of data. Well, intuitively, probably not all of that data actually matters for making our classification decision. Like we see tons and tons of examples. A lot of them are probably redundant. And what the perceptron is doing is it's sort of filtering out algorithms that were not useful in making a decision in the sense that they didn't cause us to make a mistake. So we only remember the things that we made a mistake on. And so we can sort of think of it, I think it has this kind of nice interpretation as an algorithm for kind of like selective memory. So the limitation of this procedure, of course, is that we've assumed that the underlying data was separable to begin with. And that's a very restrictive assumption in practice. Like lots of data that we're interested in is not separable in its ambient representation. So let's say, for example, that the actual decision boundary between our two classes is a quadratic. And so there exists no linear separator. And so our previous argument won't work because it was just about preserving separability to the extent that it existed in the first place, and it doesn't exist in the first place here. So there's a sort of very simple way to fix this problem, and that's to say, well, I have these original features. I'll also add in these quadratic features. So I'll look at interactions and squares of my features. And these new enhanced data vectors, we just take the original data and then we add on these extra features that we compute from it. And so the key idea is that the decision boundary, which was nonlinear on the original version of the data, becomes linear on this lifted or enhanced version of the data. And then we can just keep using a linear classifier on this enhanced version. So the basic idea is that if we want to do this in HT, then we can just compose these enhanced features with our encoding method, and we just proceed exactly as before. So, right. So the problem with this method is that by computing these pairwise products and squares and stuff, we've increased the dimension of the data dramatically. So if the ambient dimension of the data is, say, the dimension of MNIST, which is 784, then this enhanced data is actually requires 307,720 dimensions to represent exactly. So we've gone from this thing that was sort of like moderate but acceptably high dimensional to something that is really quite high dimensional. But so what we can realize is that if we look at this dual representation of our separator, so remember what we said is that we could represent the vector of coefficients as either just a vector, or we could represent it as this linear combination of embedding of data points. If we use this dual representation, then what we can see is that we only ever actually use the embeddings to compute a dot product. So right, what we said is that we have our, we've composed our HD encoding with these enhanced features, and that's just approximating this underlying dot product. And so as far as the perceptron is concerned, it doesn't care how we compute this dot product. All that really matters is just the value of the dot product. The perceptron doesn't care how we go about getting this. And so it turns out that for this particular type of feature expansion, where we look at squares and interactions between features, we can compute this dot product without needing to explicitly materialize this high dimensional embedding. So if we just do some kind of tedious algebra in two dimensions, we can see that we can actually write this dot product on the enhanced version of the data directly in terms of the low dimensional representation. And so what we're saying is that we have this function that's called the kernel function, and that lets us implicitly evaluate this dot product in high dimensional space without needing to write it down. And of course, the same trick works for arbitrary input dimensions and an arbitrary order of polynomial. So what this means is that even if our data even if the psi x, psi y live in this 307,000 dimensional space, it still only requires us amount of time linear in the ambient dimension of the data to evaluate this particular notion of similarity, which is really what the perceptron cares about for making its decisions. And so this idea is sometimes called the kernel trick, and it was first proposed in this paper by Eisenman, Braverman, and Rosenauer in 1964. And so the sort of key idea is that the only time that we ever actually use the high dimensional representation of the data is to compute dot products. So it's really just a means to an end to compute this dot product. And the coefficient vector, sorry, this W should be a theta. This coefficient vector is itself a linear combination of these high dimensional embeddings. And so anytime that we see a dot product between these two psi's, we can just replace it with the kernel function, which is easy to compute directly from the low dimensional representation of the data. The idea here is that we just store the parameter vector in sparse form. So we just remember the examples in which we made mistakes. And then we use the kernel function to compute this high dimensional dot product efficiently. And so it turns out that there are many other types of similarity functions other than this polynomial kernel that have this kind of property. So for example, there's the polynomial kernel that we saw before. Some others that people have probably seen are the Gaussian kernel, which is we already talked about in the context of random Fourier features. There's the exponential kernel, which is really just sort of, which is closely related to the Gaussian kernel. And then there's also kernels on other kinds of things that are not Euclidean data. So there's kernels, people have come up with kernels on strings, on graphs. If you can think of a type of data, somebody has probably come up with a kernel to compute similarities on it. And so the key idea is that what the kernel function is allowing us to do is implicitly work with these very high dimensional embeddings of data. So instead of explicitly writing down the HD representation and then computing the dot product on the high dimensional version, we just compute the dot product by evaluating the kernel function. So if we're limited to just these kinds of kernels that we can just kind of like sit down and pencil out, that's a bit limiting. But just like VSAs allow us to compose embeddings of data using these algebraic operators to build more complex representations, kernels also allow us to do this. So kernels satisfy a number of closure properties that let us build more complicated kernels from simple ones. So for example, kernels are closed under non-negative sums. So if we have two different kernels, the non-negative weighted sum of these kernels is also a kernel. And the feature map of this kernel, or like the implicit embedding that it's working with, corresponds to concatenating the embeddings of the two individual kernels. So when we do this, when we add the two kernels, it is as if we had concatenated the representations associated with the individual kernels and then computed dot products on that concatenated representation. We can also implement a version of binding using kernels. So if we have a pair of kernels on a set, then their product is also a kernel. And the kernel that it induces corresponds to taking the tensor product of the embeddings. So it's as if we had constructed these embeddings, computed their tensor product, and then used this trace inner product to compute the similarity between the resulting embeddings. And the thing that's cool about this is that the kernel evaluation doesn't care at all how high dimensional the embedding is. So this same trick will work even if the embedding is infinite dimensional, which it is for many of the kernels that I described previously. So the idea here is that, and I think the sort of like point of contact with VSAs is that in VSAs, we typically think of designing an embedding such that in expectation over randomness in the embedding operation, we recover a particular kernel. But kernel methods sort of go in the opposite direction. And it turns out that for any similarity function that satisfies this technical condition known as positive semi-definiteness, we're guaranteed that there exists some inner product space and an embedding that takes data from our ambient representation to that inner product space such that the kernel can be evaluated as a dot product in that high dimensional space. And so the sort of essential intuition here is that the kernel allows us to implicitly work with these high dimensional embeddings without ever needing to write them down or even or define them. So all we have to do to guarantee that this interpretation holds is that the similarity function is positive definite. And then we're guaranteed of the existence of this embedding space without ever needing to actually write it down. So we can work purely in terms of these underlying similarity functions. And so many other algorithms beyond the perceptron can be kernelized in this way. So things like SVMs, least squares regressions, PCA, k-means, and many others can all exploit the same underlying trick. So all these procedures can be described by making predictions using functions that take the form of a weighted combination of kernel evaluations at the set of training data. And so the idea is that we obtain these weights, these alphas. So by adjusting the alphas, we get different functions. And we obtain these weights in practice by minimizing some loss function over the training data. And in fact, the perceptron arises as a special case of this, in which we minimize the hinge loss using an online gradient descent rule. And typically in practice, these procedures amount to applying some sort of convex optimization problem over our training data. So the kernel perspective, and I think the sort of like real insight of the kernel methods community, is that in fact, the high dimensional embeddings for most of these algorithmic procedures are really just a means to an end. What really matters is the underlying kernel. And so this allows us to, so before I go on and talk about why I think that perspective is nice, I just sort of wanted to briefly talk about the history of kernel methods. So kernel methods have been around for a very long time. They're well studied in functional analysis, and the kind of foundational theory that led to modern techniques like support vector machines and kernel PCA and stuff was laid down in the early 1950s. They were sort of their use in statistics and machine learning was first pioneered in the 70s by this statistician named Grace Waba and some of her colleagues. And they really exploded in interest in the 1990s with the development of support vector machines by Vladimir Vapnik and Bozer. And I guess it's sort of worth mentioning that these techniques have recently seen a resurgence of interest as a tool for understanding deep neural networks. So people have sort of tried to develop theories for how and why deep neural networks work based on our understanding of kernel machines. So I think the reason that kernel methods are a sort of appealing way of thinking about problems is that it allows us to separate modeling assumptions from the computational realization of our model. So we have these sort of fundamental modeling questions, which are like, what notion of similarity is appropriate for my task at hand? What kinds of functional relationships in my data can I possibly hope to learn given a particular choice of similarity function? And then also, what is the statistical hardness of learning them? And so these are really questions fundamentally about kernels. And kernels let us reason about these types of questions in a manner that doesn't depend on the sort of particulars of how I go about computing the kernel. And so so for our perspective, that means that these are sort of abstract questions about the underlying notion of similarity that we're interested in, as opposed to the particular way that we construct a VSA that gives us that notion of similarity. So kernels are also appealing because the computations are exact. There's no, these are just noiseless deterministic computations. And they sort of use this like superposition principle, but in a manner that doesn't suffer from any crosstalk noise or anything. So the question is, this all seems very nice and provides us with this sort of nice abstract theoretical framework, but what is the cost of doing this? And so basically the idea is that the kernel trick allows us to work in very high dimensional spaces. So we can capture these sorts of very rich types of similarity using kernel functions. But the cost of this is that we have to store raw data to evaluate the prediction function. So remember we said that like when we're doing the kernel perceptron, we remember all of the points on which the kernel made a mistake. Or if we're doing a support vector machine, we need to remember all the support vectors in our data. And what this means is that in order to evaluate these kernel machines, we have to store data and we have to access it repeatedly to compute the kernel function. So we've saved ourselves the problem of working in these sort of very, very high or even infinite dimensional spaces at the expense of needing to store raw data. And so in particular, so this is maybe not such a problem if these coefficients are very sparse. So if our perceptron if the margin of our data is very large and our perceptron only makes a handful of mistakes, then this isn't really that big a problem because we don't need to store very much data. But as is often the case in practice, if these alphas aren't that sparse, then this can be a real problem. And so in addition to this problem of memory, we also potentially lose out on other benefits of these distributed representations. So for example, it's not clear that these kernel methods are natively fault tolerant. It's not clear that they're amenable to computation using low precision, and it's not clear that they can be computed in a highly parallel way. So one question we might have is there a way that we can retain some of the benefits of the kernel perspective, which is that it provides us with this sort of very nice theoretical abstraction, while also retaining the benefits of distributed computation? And the answer is that yes, we can. And distributed representations provide a mechanism to develop efficient realizations of kernel machines. So the basic idea, right, is that kernel machines or kernel methods like SVMs or kernel ridge regression give us functions that look like this. They look like weighted combinations of kernels centered at our training data. And so if we can design a distributed representation of finite dimension such that dot products between the distributed representations approximate our underlying kernel, which as we've seen, we do all the time already in VSAs, then we can just sort of then, instead of explicitly storing these data points, we can store them in superposition by smushing together or bundling together their weighted embeddings. And so what this means is that we can express an approximate variant of this kernel machine as a dot product between a vector of weights and an embedding of a data point in this finite dimensional HD space. And so in a certain sense, to a statistician, we might view VSAs as a low dimensional approximation to some infinite dimensional ideal model. And the basic intuition here is that what we've done is saved memory and compute resources at the expense of introducing some approximation error. So we no longer are able to fit the exact kernel machine, but that probably wasn't really that important anyways, because usually our data has some sort of notion of wiggle room, like a margin or something in it, that means that these computations of the kernel function don't need to be exact. They can be fuzzy. So the kind of fundamental intuition here is that we can efficiently approximate kernel machines by solving linear learning problems in HD space. So if in HD space we fit, say, a perceptron or a linear SVM or a ridge regression, we can interpret this as fitting a kernel machine using the underlying kernel that is approximated by our encoding. And the reason that this is nice is it allows us to do this very efficiently using this sort of superposition principle. So here again, there's a broad family of work on this in machine learning. And these techniques are often called random feature models. So in machine learning, this technique was popularized by in a series of papers by Rahimi and Recht that came out in the late 2000s. And this area still remains a really active and popular area of research. So even today, there are still people who are publishing things about these kinds of random feature models. And so I think it's sort of interesting to note that the VSA community, in a certain sense, was actually a really early pioneer of this kind of an approach. And it may not have been sort of explicitly explained as such, but I think the reason that we were, I shouldn't say we, because it wasn't me, but the reason that the VSA community was sort of saw promise in these methods is sort of for very similar reasons that computer scientists did subsequently. Right. Okay, so the basic premise of this talk is that computing with high dimensional vector representations of data is in fact a sort of central part of the machine learning canon. And the most visible manifestation of this is in kernel methods, in which we do all this computation implicitly. So in kernel methods, we say, okay, what I really care about is just the notion of similarity that is implied. And so instead of working explicitly with these high dimensional representations, I work implicitly with them via the kernel function. And the cost of this is that I lose out on all of the benefits of distributed representation. But what we can do is say that, well, in fact, these distributed representations allow us to retain these sorts of theoretically appealing properties of kernel machines while providing a scalable and efficient implementation of them. And it's sort of worth noting that there's a large and active area of research on this topic in the broader machine learning community. And that's probably a good place for us to look for some theoretical insights into the functioning of VSAs. And so I think kind of at a very, sort of at a very high level, I think of these things as sort of like, different levels of how connected to the representation you are. So in VSAs and HD computing, we're very connected to these representations. Like we're tied very closely to the particular instantiation of our encoding procedure. And then there's this sort of spectrum of other sort of views on this problem that allow us to take a slightly more abstracted approach. So in kernel approximation, we say like, okay, well, we still want to actually materialize these representations, but now really all we care about is this kernel preservation property. And then we can go even one step further and say in kernel methods that we don't care about the representation at all, and all we care about is the underlying notion of similarity. And so my view is that this abstract kernel perspective is helpful for reasoning about our basic modeling assumptions and the sort of fundamental capabilities of information processing tasks expressed on VSA representations. but the concrete representation is necessary and helpful as a model for distributed computation and giving us these kinds of computational benefits that we like about VSAs. So I know that was a ton of material to try to fit into a 15-minute talk, but I hope that that was helpful for people. And yeah, I'd be happy to take any questions if there are any.
Anthony, thank you. Thank you very much. So any questions from the audience? Tony, you are unmuted.
Yeah, Anthony, this is fascinating stuff. I love the idea of looking for connections and inspiration here. One thing I wonder, have you seen anything that could give insight into how to think about things like information density and how to think about quantization in distributed representations from looking at this connection to to very high or infinite dimensional kernel methods?
Right. Okay, so I think that's a really good question. So the answer is yes. There is, so in particular on this literature on random Fourier features, let me go all the way back to it. There's been a lot of work thinking about how to come up with low precision or quantized versions of random Fourier features. I've suggested a couple papers here that I think would be good places to start. So, and so basically what these procedures do is they construct the full precision random Fourier feature and then quantize it. And we can think of the quantizer as adding noise to the underlying features. And so we can incorporate how much noise can be tolerated into this model of how well the kernel dot products in HD space preserve a particular kernel. And in fact, I'm sort of working on a paper that looks at some of these issues, and I'm hoping to put it on an archive in the near future. And so I think the second part of the question was about thinking about information density. And so I think that, one of the reasons that I think that this kernel perspective is sort of nice is that it allows us to abstract away a little bit from this question of like storage capacity and information. Because really what we're saying here is that we have some sort of underlying kernel function that we're interested in. Like if we had an infinite number of features, if we had an infinite amount of data, we would be able to fit this perfect idealized kernel function. And so really the question we can ask is, how well does our randomized approximation approximate this kernel, and what are the implications for like model fitting in HD space? So for example, if we minimize over the class of linear functions in HD space, what we are really interested in is how good an approximation is that to this underlying kernel function. And so I think that we can answer these questions just in terms of how well dot products in HD space approximate the underlying kernel. And so it provides us with a way to kind of take a more abstracted view than worrying about, like how many, like these sort of notions of information density and capacity.
Okay, thanks.
Some more questions? So let's see. Maybe I have a question of my own. Sorry, maybe it will be a little bit naive, but for some embeddings, we know the underlying kernel, but other embeddings, so how to understand what kind of kernel the specific embedding approximates? I don't know if it makes sense.
So you're saying that like I construct these atomic embeddings, and then so for the examples that I described here, we can just write down what the underlying kernel looks like. But in other cases, perhaps if we bundle and bind things together, then we can't do that.
Yeah. So for example, random Fourier features, and fractional power encoding, so they relate somehow.
Right.
But if I start with some random vectors and then I use VSA machinery to encode a certain input in some complicated way, so how do I understand what kind of kernel I approximate at the end?
Right. So I mean, I think usually the idea is that we construct the bundling and binding operator so that we can interpret what we have done with the embedding. Like we've designed the sort of, at least to my understanding, what it's sort of like explicit aims of this algebraic structure so that we can sort of follow a chain of reasoning that allows us to like figure out, like track what happens to the kernel as we do these more and more complicated bundling and binding operations. Now that's, you know, so I think even in a case in which we don't know exactly what the underlying kernel is, we know that there exists some underlying kernel. Like it's, in fact, it's just mechanical, that like if you look at dot products between encodings, that generates a kernel, it just does by the definition of a kernel. And so in expectation over randomness, like there must be some kernel arising. And so we can still use these kinds of tools to understand like how increasing the encoding dimension would improve the fidelity of approximation of this underlying notion of similarity, whatever it may be. And so right.
Yeah, sure.
Yeah, sorry. No, go ahead.
No. You finish.
Yeah, I think so. I think those are sort of my two views on the problem, I guess, is that the machinery is still useful, even if we can't just write down in closed form what the underlying kernel looks like. And I think one of the things that's nice and appealing about VSAs is that it allows us to sort of track what we're doing as we build up these increasingly more complicated representations of objects.
Yeah, makes sense. Absolutely.
Yeah, so I had another question on the relationship to the kernel spaces here, and that's, do you see any? And so this is about normalization, which, you know, when I've experimented with distributed representations, normalization often seems really useful in terms of keeping the representations under control and not exploding in strange ways. But it seems sort of like a bit of an unsatisfying hack. And I was wondering whether there's any, if you look at it in terms of the kernel space, does normalization play any role whatsoever? Is there any correlate, or is there a different way of looking at keeping the sort of magnitudes and of the representations under control?
So I think that I guess my intuition for why normalization might matter comes from this sort of like, you know, pencil or like back of the envelope calculation that I've given here, where the dimension that we need to ensure a particular fidelity of approximation depends in part on some notion of like boundedness in the embedding function. And so if we can ensure, and so, you know, there's actually sort of other variants of this that we can do, that where if the embeddings are unit vectors, then we can obtain better concentration properties. And so I think that preserving this kind of normalization helps us to obtain faster concentration. And so in terms of the kernel function, that's a good question. If they're, you know, I mean, so part of the idea is that the kernel perspective is to not really, it doesn't really matter what the embedding actually is. Like what just matters is the dot product between them. So I don't really know. I guess the short answer is I'm not sure I answer that question.
Right. Yeah, and is it the dot product that matters rather than the cosine? So it's an unnormalized dot product, you're saying, right?
Right.
That's what I was thinking. So normalization doesn't really appear there. Yeah.
Right. Yeah. It's an unnormalized dot product.
Yeah. Okay.
All right. point. Let's check if we have more questions.
There's a question from Alexander in the in the chat, Evgeny.
Oh yes. But maybe Alexander, you can vocalize it yourself. You're still here, right?
Yep, I am. I'm just trying to get this damn thing working on my phone. So, yeah. So about underlying kernel, is there only one or many in the data? I'm having a bit of maybe trouble with that notion, because to me, just data is a point of clouds, right? And then you just define similarity functions on it, and they could literally be anything.
Well, so for kernel methods, they can't literally be anything. They have to satisfy this property of positive definiteness.
Yeah.
And one can come up with reasonable notions of similarity that are not positive definite. Okay, so the question is so maybe there's two parts of the question here. So what do I mean when I say underlying kernel? What I mean when I say underlying kernel is that different encoding architectures generate different kernels, and each encoding architecture is associated with a particular kernel. And so that's what I mean when I say underlying kernel. Now, I think there's another part of this question, which is like, how do I choose the kernel for my data? So of course, as you allude to, given a bunch of data, there are many ways I could choose to measure similarity between points. I could choose to use the Gaussian kernel. I could choose to use a polynomial kernel. I could choose to do many different things. How do I choose between these? So I think, much sort of like the philosophy underlying VSAs, one answer to this question in the kernel literature is to say, well, you should use some sort of domain-specific knowledge about your problem. Like, I have understanding of my problem, and so I will explicitly incorporate that knowledge into my modeling of the problem via my choice of kernel function. So I think, that's sort of one way of doing things. The other way of doing things is to say, well, I can interpret these kernel machines as curve fitting problems. So I'm defining a particular class of functions by my choice of kernel, and then I'm just applying an optimization procedure to select a function from that class. So what I will do is say, like, well, maybe it's too hard for me to come up with a kernel that really incorporates my understanding of the problem or whatever. So I'll just pick a very powerful general kernel that induces a very rich class of functions. So some of these kernels, like, for example, the Gaussian kernel, they're associated with very, very rich classes of functions. So using these types of functions that look like weighted linear combinations of kernel evaluations with the Gaussian kernel, you can, in a certain sort of asymptotic sense, represent any continuous function. And so the sort of more like data mining oriented view of this is to say, I will just choose a very, very powerful kernel, and I'll just worry about overfitting and control it through regularization. And so, so you're right. I mean, I think that, the question you're alluding to is really one of the fundamental challenges of kernel methods, and that's how do you go about picking or designing a good kernel for your data? And yeah, so I think, it's a good question. And there's sort of lots of different strategies that people have come up with in practice. And the sort of two that immediately spring to mind are this approach of choosing something very, very powerful and relying on regularization to deal with overfitting, or sort of like explicitly trying to incorporate domain knowledge into the kernel.
It's very modular, the whole thing, isn't it? It's actually frighteningly modular, because you start with a point cloud, then you can think of a function which maps anything to anything. It could be, in principle, anything. It doesn't even need to be analytical. So there's a huge sort of freedom factor in there. And then you end up with some kind of mapping, and then we are talking, or at least the way I understand it, probably rather naively, in terms of optimality. And there you can start choosing from families which are more or less generic or powerful, like the Fourier transform or the Gaussian stuff, which you alluded to, which makes me think of wavelet transforms and all of that kind of stuff. And they can be generic and have very nice properties and so on. And on top of that, they can also have, since we are talking about mathematics now, they can have infinite resolution, and you can, you see what I mean? It's very interesting, at least yeah, for me, that kind of
Right.
brain dump, I hope, was interesting.
Right. No, I mean, I think that sort of modularity is what makes them very appealing to a lot of people, is that you have sort of separated this problem of representation from the problem of learning from the representations. And that allows you to sort of like reason about these two things as independent pieces, which makes a lot of problems, which simplifies a lot of analysis problems on them. And yeah, I mean, I think that sort of modularity is sort of the beauty of kernels, that they allow you to think in this sort of very like, so, you know, as you alluded to, there it's an incredibly general family of techniques. Like the embedding function can be basically anything. You know, like you can induce the kernel via essentially any sort of embedding operation, and so that makes them a very sort of powerful theoretical framework in which to think about these types of models that broadly conform to that sort of template.
Makes sense. Thanks.
So maybe a few more questions, if any.
I've got one. Excuse me. Sorry. Thank you for that. Anthony, I'd like, I'm going to ask a question which is really just an appeal to your obviously broad knowledge of this, the kernel literature, to see if a particular problem that I'm interested in has been addressed within that literature. So this gets back to what I tend to think of as the difference between dynamic and static similarities. So when we're talking about kernels here, the notion is that the kernel is, you know, once you've learned to solve some particular problem, the kernel is fixed over all the possible data pairs that you might consider. So the similarity there is static. But let's say you're doing something like trying to find the similarity between images, but you want to allow for the fact that, you know, the same image can be rotated or scaled or translated and so on. But you're not clever enough to come up with a kernel which is invariant to all those different transformations of the images. So one way you could deal with this is within your kernel function, you've got the two objects you're comparing. But you think of one of them as being in memory and one of them being a current object. You could apply a transformation to that query object to scale it, rotate it, translate it, etc. And so what you're interested in, though, is that alignment function. You do the argmax over that, over the parameters of that in real time. So that's sort of your dynamic similarity aspect. So you're sort of the kernel is between the optimally transformed input and some other value. So I'm just wondering whether that notion of, you know, transformation outside the kernel, but to optimize, to maximize the kernel similarity that's computed, whether that actually turns up anywhere in the kernel literature, or whether you just say, well, no, the correct answer is you come up with a kernel which is invariant to all those transformations.
Okay, so what you're saying is that you have a kernel, and you have like a reference image, and then given a query, you want to kind of apply this transformation. You want to like look for the transformation that maximizes the similarity to the reference.
Yeah.
As determined by the kernel.
And then effectively, you know, the similarity value returned from the kernel is saying this is the similarity of the reference to the optimally transformed version. Right.
I don't know about anything off the top of my head that does that. Sorry, I don't know. But so I think, you know, the maybe a sort of related problem is like, well, what if instead of like, you know, okay, so it's a lot to expect that there is a single fixed kernel that is always correct in perpetuity.
Yeah.
So it would be nice if we had some way of introducing at least a little bit of adaptivity into the choice of kernel. And so there's a long line of work on what's called multiple kernel learning, which is where you say like, okay, I have a large dictionary of possible candidate kernels, and then I want to choose like which one of these kernels I should be using at a particular moment in time. And so there's a big line of work on like efficient algorithms for doing that.
Okay, if it's given that you're at Redwood, if you had any interest in that that topic, have a word with Bruno Olshausen about the work of David Arathorn on map seeking circuits, because that's essentially that problem. Be interesting to see where, whether there was a kernel. Sorry, was that you, Fritz?
Yeah, absolutely, Ross. But of course, he does not really much dwell on the concept of kernels. But of course,
no, not at all.
Computes in a product. I mean, yeah. I mean, yeah, it's a good point. We have to search the literature. Maybe there is actually maybe there is actually something on these kind of invariance problems in connection to kernels. I am just also not aware of any literature that does this.
Okay, no, well, if anybody else can come up with any pointers in that direction, I'd certainly be interested. Yeah, thanks very much for that.
All right, I look at my clock, so it's 10 minutes past 10 p.m. at least since we're in Europe. So, and it's time to wrap up. So thank you very much, Anthony, for your great talk. And indeed, it was really great. And I think we need such a material to make VSA understood outside the community. So absolutely. So that's has a great value. And thank you all for attending. So see you in 2 weeks from now.
Thanks. Yeah, glad you.
Yep. Bye-bye.
Have a great week. Bye.
Yeah.
Bye.
Thank you.
Bye.
Great talk, Anthony. Thanks.
Thank you. Thank you.